this. We will these two things we will do in this class. Okay, so why this is still the routine? I will directly write the results because derivations we have done already. So those things we have done. Who got disconnected? Yes, Tarif, welcome back. So you got disconnected, right? Got disconnected. Yeah, your voice is lagging so much. Yeah, so okay. Yes, can you hear me, Tarif? Yes, can you hear me? Hello, Tarif, can you hear me? Yes, yes, okay, yes, Tarif, can you hear me now?
Uh, Yes, sir. Sorry, sir. I don't know. Suddenly, in
Mm.
the night, the Wi-Fi becomes bad.
Yeah, yeah, yeah. So I can totally understand. Sometimes it also happens with me as well. So no worries.
So I
Okay.
guess because everyone is starting to use the Wi-Fi I use, so that's
Yeah, yeah. So okay. No, okay, don't worry about that. So let us quickly start right here. Yeah. So force on a current, we have already talked about magnetic force, right? We have a charged particle that is moving with some velocity. So then what is the force? That is magnetic. That magnetic force we have already calculated. Now we have a current carrying conductor. So we have a current carrying conductor. So what is the force on a current carrying conductor? right? So let's say we are representing the magnetic field like this. So this shows that the magnetic field is acting inwards, right? They are going into the board, into the screen. So we have this magnetic field, and then we have this current carrying wire, which has a length L, right? So this is I. So in this case, what would be the force on this current carrying wire experienced due to this external magnetic field? So that is related as I L cross so that right. And if we write the magnitude part, so that is I L P sine theta, the angle between the current and this length and this magnitude. So that is the force. Okay. Similarly, let's say that if we have two right, so two parallel wires, and we have to calculate the force between them, right? So we have two parallel wires, and there is no external field in this case. The external magnetic field is not there. So the magnetic field will arise due to each current carrying wires, right? So the magnetic field will arise due to each current carrying wires. So let's say this I1, this is I2. So let's say this distance is A, okay, and the length of the wire is L. So we'll talk about that later. So you see that if I calculate the magnetic field at this point due to this I current. So this is an infinite wire, right? Infinite wire, and I have this point. So what would be the magnetic field in the right hand side? Yeah. So shall we just yes, hello Shavi, assalamu alaikum. So we have just started, right? So today I'm talking about the force on a current carrying conductor. So first we are taking a conducting wire. So on conducting wire, the force is IL cross B, right? Similarly, we are talking about two parallel wires. So force between those two parallel wires would be how much? So let's say we have this I1 current,
Sir,
and
can you hear me?
yeah, yes,
Can you hear me?
yeah, this is the thing that we are.
Can you hear me, sir?
Yeah, I can hear you. Yes, I can hear you. Yes.
Sorry, sir, I'm out now.
Oh, you are outside. Okay. Okay, no worries. Then, yeah, then, yeah, just then you cannot note it down, right? Then just this.
Sir, I'll take screenshot.
Yeah, you take yeah, please take screenshots. Okay. So first, we are talking about the force on a current carrying conductor, right? So we have this current carrying conductor which is placed in outside magnetic, right? So the force experienced by this current carrying conductor would be IL, right? So IL cross B, and this is IL B sine theta. So now we have no external magnetic field, but two parallel wires. So we know that due to this wire, right? Due to I1 wire, the magnetic field will be generated at this point, and that would be in this direction, right? So due to I1 wire, we will have the magnetic field right? So we have a magnetic field like this. due to I1 wire. And how much is that? How much is that, guys? Can you recall? What is the magnetic field of this infinite wire?
I1 L cross B sin theta.
So that is the force. That is the force. I'm talking about the magnetic field due to this infinite wire.
Yeah, mu naught I by 4 pi r.
4 pi r. That is
Sorry, sir, 2 pi r.
pi, right? So mu naught I1 by 2 pi and let's say E. And this is in the inside direction. So that is inside, right? So we have these magnetic fields, right? We have these magnetic fields, and the length is like this. So this is, let's say I take this length, right? I take this length. So length is going in this direction. Length is j hat, right? The direction of length, and magnetic field direction is what? Inside is what? Minus k hat.
Minus I k cap.
Yeah, minus k cap. So now we have this length and we have magnetic field. So the force experienced by this I2 wire, right? Force experienced by this I2 wire due to I1 current. That would be I, right? I2 and L cross B. So let's say ILB sin theta, right? And what is the angle between them? So this is inside and this is upwards. So angle is how much? How much is the angle? 90 degrees, right? One is inside, magnetic field is inside, this is upwards. So one is in the y direction, one is upwards, y direction, the other one is inside, right? So what is the angle? 90 degrees. This is going inside towards you, and then this is upwards. So 90 degrees is the angle, right? You guys can also see from this part that it is j hat and k hat. So what is the angle between j hat and k hat? That is 90 degrees. So theta is 90 degree, right? And I2 is this, L is this, P we know. P is mu naught I1 divided by 2 pi A. So magnitude would be how much? F21. This is mu naught I1 I2 divided by,
Sir, it should be I1, right?
yeah, I1 I have written I1, right?
No, sir, that I2 into L cross B road, sir.
Yeah. So you see that I am calculating the force on this wire, right?
Oh, okay, sir.
So, yeah. So I2 current I will take and magnetic field is,
Sir, force is on I2, sir.
yeah, force is on, so force is on 2 due to 1, right? Force on 2
Okay, sir.
due to 1, right? Clear? Yeah, so
Yes, sir.
this is L, and let me write it as F, because this would be equal to F1. If we calculate this thing, we will find out that these two are equal. So this, let me write it as F, and then force per unit length. Per unit length, that would be how much? That would be F by L, and this is mu naught I1 I2 by 2 pi. So always remember this is a very important relation. Now we have to find out the direction, right? So now we have to figure out what would be direction. So for direction, we know
Sir,
that,
force per unit length means the force on uh, unit length.
yeah, force on a unit length, right? Force on a unit length. So let's say the total length is 2 meters, So we are calculating the force on 1 meter length. So that is force per
Okay, okay, sir.
meter. So now we want to find out the direction. And direction, we know that that would be L hat cross B hat. That is the direction of F hat, right? So L hat is J hat, and this is minus K hat. So minus, I can take it in this side. What is J cross K, guys? What is J cross K? If we apply the circular cyclic property,
I cap, sir.
I cap. So we are going in the clockwise direction, so that would be positive, so I cap. So now you guys see that this I1 current is applying a force in this direction, right? Right, guys? So that is what kind of force? Repulsive or attractive?
Sir, attractive.
Attractive. So you see, whenever these currents have same direction, so whenever, yeah, force would be force would be attractive if I1 and I2 have same directions, and vice versa. So if they are opposite, then that would be repulsive. Okay. So these are the things which are very important, and then we'll do one question to understand this thing properly. So you guys please note this thing down, and then we'll talk about the talk. So I will just write the result, and yeah, guys please note down this thing. And whenever you guys want me to scroll down, please let me.
Done, sir.
Yeah. Yeah, so you are taking this screenshot, right? So maybe Tarif will take a longer time. This is another, right? Just to tell you that.
So 1 minute, can you scroll up?
Okay. Yeah. So if we and these kind of examples, you should not bother about this derivation. Yeah, you just write these formulas and just. And yes, hello guys, you are here for share. Okay, yeah, whenever sorry if you want me to scroll down, please.
Can you scroll down?
Yeah. So whenever you guys have noted it down, then we'll do one question to understand the thing, and then we'll go to the torque part. Yeah. Whenever, sorry, you have noted.
On. Sir,
Yeah. Okay. So let us do one question, and then this would be easy to understand. Okay. So we have two wires, and as you guys can see that they are not parallel; they are anti-parallel, right? So two wires A and B are carrying currents I1 and I2 as shown in the figure. The separation between them are T. A third wire C carrying a current I is to be kept parallel to them at a distance x from A, such that the net force acting on it is zero. The possible values of x are. So this we have to find out, right? So a third wire carrying a current I is to be kept parallel to them. So at C point we have to put a wire, right? So we have this thing, right? So let's say we have one wire, and this is I1, right? We have another wire which is we have to place. So let's say it's current direction. This is the current direction. And we have another wire, right? This distance is d, right? So we want to calculate A third wire C current placed at a distance x from such that net force acting on it. So we want to calculate the force acting on this wire, right? So let's say this distance is x. So this distance would be how much, guys? This distance would be how much? Yes, guys, this distance would be how much?
D minus X.
So this would be d minus x, right? And we know that we are calculating the force on this wire, right? If this is the direction, if this is the direction, so this will try to pull this thing, right, towards its direction. And if I'm calculating due to this force, so this will try to move this thing in this direction, right? Right, guys?
Yes, sir.
So, and both these forces will give me net zero force. So F net is 0. This is FA and this is FB. And FA plus FB is 0. Right? This is what we are getting. Right, guys?
0.
Yeah, so this would be 0. Because F net is 0, right? The separation between them, our third wire is kept at distance x, the possible values of x, right? So either we place a third wire C carrying a current I is to be kept parallel to them at a distance x from A such that net force acting on it, right? So there are two forces acting on this wire. One would be this, and due to this wire, this would be this direction, right, guys?
Yes, sir.
Okay, so what would be FA? Let us calculate FA. How much is this? So that is I1, I mu naught by, let's say, 4 pi, not 4 pi, but pi, and this distance is x, right? And let's say some length that we are taking. So that can take. So this is FA, right, guys?
Yes, sir.
Similarly, if B would be how much? That would be mu naught I2 IL divided by 2 pi and D minus x, right?
Yes.
So if we sum these things, so if we take F net, so this would be mu naught I1 I and 2 pi x L plus mu naught I2
Sir, we can
and
take mu naught I1, I2 by 2 pi x common, right?
yeah, we can take that.
2 pi.
Yeah, so that thing we can take from. Yes, absolutely right. So this is L. We can take this thing common, right? So we can take mu naught I L by 2 pi, right? This thing we can take common, so we'll get I1 by x plus I2 by d minus x, right? This thing we get. So this thing is a constant. We can take it out in the other side. So we have I1 by x equal to I2 minus d minus x. So we can take this thing in this side. So this would be I2 and x minus d. This minus I just take this in this inside. So this would be how much? I1x minus I1d. right? And then this is x I2. So if I take I1x minus x I2, and this is I1d. So what I will get? I will get x common and I1 minus I2 and I1d. So x is I1d divided by I1 minus I2. And yeah, so this would be positive negative. Why? Because I have assumed that this is my current direction. So I have assumed in this direction, then that would be negative, right? So then this would be negative.
Sir, can you repeat?
Yeah, so you saw that what did I assume? I have assumed that my current direction is this, right? My current direction is this. So I am getting this plus thing, right? But I can also have this current direction in downward, parallel to this thing, right? So then
Yes.
in that case, the F net would be in this direction. So then I will get, yeah, then I will get a negative sign here. So that is what I am saying. Okay, because in one case my current is positive, and the other case my current is downward, so I can take it as negative. So I will have positive and negative. So option is this thing clear, guys? Is this thing clear? Yes, you
Yes.
guys. Yeah. So please note this thing down. And if you guys have any doubt, please ask. But remember, if this I2 was in the parallel direction, then it would have gotten a different answer. Yeah, whenever you guys want me to scroll down, please.
You can scroll down.
Yes, whenever you guys have completed these,
Yes, certain.
done. Okay. So yeah. So now we talked about uh, force on in an external field due to in a current carrying wire, and then we talked about two parallel wires. Now what do we do is that we calculate the force on a loop, right? So okay, so we have a loop, right? We have this loop, and the magnetic field is passing right. So then we are calculating a force on this wire, right? So on this loop carrying a wire, and you guys have seen that. What is the force that you guys get? What is the F net that you guys get? So magnetic field, right? You know that this one is perpendicular to this one, right? So this thing, if you calculate all these things, so you find out that this would be zero, right? You calculate these things, so you will find out that F net is zero. But this creates a net rotating effect, right? So loop, for this loop, we calculate for this loop, for this loop, we calculate net dipole moment. So magnetic dipole moment we calculate. So for a loop, we calculate net diamagnetic dipole moment, right? And that is represented by M. And this is a vector quantity. It is given as N, uh, N, I, and A, right? So the direction of this dipole moment is what? This is in the direction of the area, right? So if you calculate the area vector direction, so that would be the direction of this dipole. Okay, is this thing clear, guys? So this will have a dipole moment in outward direction, right? Or we can also, yeah, so this is going like this. So we can also use the Maxwell's thumb. So if we rotate our curl in this direction, so we are getting inward direction, right? So magnetic field and area vector would be inwards. Right? So if we are getting in this direction, so if we are going in A, B, C, D, A, so the dipole moment would be inwards. right? And this n here is the number of turns. This n here is number of turns, and this is the area of the. Okay. So due to the net dipole moment, due to this net dipole moment, we have a torque. So let's say we have this loop which is inside a magnetic field. So let's say we have this magnetic field and we have placed this current carrying, right? So this current carrying loop has this magnetic moment, and this is the magnetic field, right? So let's say if we place it something with some angle. Let's say if we place it with some angle, something like okay, so this is the direction of the magnetic moment. So the torque due to this thing, torque would be right. So this has a direction m. So torque would be m cross, and this is mb sine theta, right? But remember, this is quite different from this dipole moment or dipole strength is quite different from this dipole, right? P. So this P is different from this M. Okay. So as you consider, so this P is how much? This P is how much, guys? Can you guys do you guys remember? This is how much? Yes. If you have a dipole,
Q into 2s.
so yes. What do you say?
Q into 2, yeah.
Yeah. So this is Q into 2, right? And P hat. So what is this? Now you see that this is not Q into 2a. This is something Ni, right? So how this is related with this P? How is this analogous to this P?
Sir, in magnetic field and electric.
Yeah, that is very, very much related, right? That is very much related because we have seen that torque is P cross E, right? And in here we are getting a torque which is M cross P, right? But this P is 2QA, but this M is NIA, right? So how this is related with this poles, right? This is related with this poles by this magnetic monopole, right? So if I write this is a charge, so if I assume a monopole which is south and north, so the direction of magnetic monopole is in this direction, right? So this is my M direction, and this is defined as this is M into 2 L. So let's say if this distance is L, so this is M into 2L. So this is how this M is related, where this is the magnetic monopole, right? So if you want to calculate this magnetic monopole, so you just divide this by 2. That is how you calculate the magnetic pole. So remember, this M is quite different from this M. This is the dipole moment, and this is the magnetic monopole. Okay. So if so, whenever we write the analogy from this dipole moment, so similarly, if we have so analogy from dipole. So let's say if we have a bar magnet like this, and its magnetic moment is in this direction, right? And if we are calculating the magnetic field at the equatorial point. If we are calculating the magnetic field at the equatorial point, so what would be the magnetic field at this is the axial point, right? This one is the equatorial point. So this is equatorial, and this one is the axial. So B axial, as we know that E axial is how much? This is 2 kp by r cube, right? Right, guys? And k is how much? K is 1 by 4 pi epsilon naught p hat by r. So similarly, analogous to this thing, we have a B axial which would be 2 and mu naught by 4 pi m by r. Here guys, similarly B equatorial would be how much? B equatorial would be mu naught by
The
4
logos
pi.
of E equatorial.
Yeah, so analogous to E equatorial, right? So that would be this, right? So because what is the E equatorial? This is Kp minus pi r cube. So this would be minus mu naught by 4 pi m by r, right? M by r cube, 2m by r cube. That is the difference. So what did we learn? We have learned that we have for a loop we have a magnetic dipole moment which is NIA, and this is equal to number of turns. So if we have n number of turns, then this would be this thing, right? And so this is how we calculate, right? So this loop will create a torque, right? This loop will create a torque, so this is going in this direction. So this loop will create a torque, and that torque would be this thing, which is very analogous to the electric effect. And as we had this charge monopole, so charge we can write as plus Q and minus Q. Can we write the magnetic monopole? Can we write that? Right? We cannot.
No,
We
no.
don't. Yeah, we don't have a magnetic monopole, right? Because the magnets will always come in pairs. So
Dipoles.
magnet will always have a north and south. You cannot distinguish, or you cannot write, or you can divide them separately. For a charge, you can have a plus Q charge and minus Q charge independent. But for a magnet, you cannot have a north pole and a south pole independent. So if we take the analogous of this magnetic monopole, then we can write this. But we will always write this as magnetic dipole. And magnetic dipole is Ni. So always remember this thing. and then we can take this analogy. So this is very important. This always comes in the exam, right? If you would be given something like this, right? And this is the magnetic dipole moment, right? So sometimes they denote it by M and sometimes they denote it by M. So always remember that magnetic dipole moment is this, right? So magnetic dipole moment is this, which means that this would be south and this would be north. Always remember this, right? So yeah, remembering this thing, then yeah, then we'll do some numericals based on this. So please note this thing down, and then we will do some. Okay, I have not calculated this part only, but this calculation you guys already know. So I have not shown that why this definitely is right. So yeah, you guys please note down this. Yeah, whenever you guys want me to scroll down, please tell. Yeah, whenever you guys want me to hold on, please. And direction, how do we can determine the direction? So direction is right hand thumb, right? So you curl your fingers and whatever direction you get. So for this case, if we curl, so these would be inputs. So that is magnetic dipole.
So it's same as magnetic field.
Yeah, no. So magnetic dipole moment direction for
Okay.
this for this loop for this loop, right? Yeah, whenever you guys want me to scroll down, please tell me. You want a couple of questions. Yeah, Tarif, noted. Oh, Tarif got disconnected. So please note it down. Yes, taken the screenshot, Chavez. Yes, Chavez, taken the screenshot.
Let us.
Oh, so Tarif
So,
oh, this part you are noting. Please note it down and then you have to do a couple of questions, right?
yes, sir, can you scroll down?
Why are you seeming to be tired?
Yes, sir.
Why are you appearing to be so tired? What happened?
No, sir, nothing, sir. Nothing happened.
Yeah, please quickly note it down and then you will
Yes, sir.
come. Yes, Tariq, noted.
Yes, sir. Done.
Okay, so now let us do some problems to understand. This is the question. So a coil is the shape of an equilateral triangle of sides 10 centimeters. Lies in a vertical plane, the pole pieces of permanent magnet producing a horizontal magnetic field 20 millitesla. Right, so we have a coil in shape of an equilateral triangle of side 10 centimeters. This is a coil. Right, lies in a vertical plane and of permanent magnet producing a horizontal. So we have this horizontal magnetic, right? So B is how much? This is 20 millimeters, right? So the torque acting on the coil when a current of 0.2 ampere is passed through it and its plane becomes parallel to the magnetic field with this nanometer, right? So Newton meter. So is the pass through it and its plane becomes parallel to the magnetic field will be this nano Newton meter, right? So the torque acting on it becomes this torque becomes this. So we have to find out the torque of this thing. So we know that this is an equilateral triangle, and let's say the current is flowing in this way, right? So if the current is flowing in this way, uh, then the dipole moment would be inwards. So dipole moment would be inwards, and we have this magnetic field which is right hand side. So this would be dipole moment is inwards. This is M, and this is magnetic field. So torque would be simply M B sine theta, and theta is how much? That is 90 degrees. So torque would be simply mb, right? So we have to calculate m. B is given. B is how much? B is 20 milli is 10 to the power minus 3 Tesla. So we know B, and m is how much? That is I N I A. So N, there is only one turn. I is how much? I is 0.2 ampere, and area is the equilateral triangle. So what is the area of equilateral triangle? What is the area? Yes. What is the area
Half
of
basic height.
half base into height? But height we don't know, right? So the simplest way to remember an area of triangle is, let's say you know this thing, and you know the angle between them. So the area of triangle is simply half A B sine theta. right? So for an equilateral triangle, what is this side? A and angle is 60, right? Is that correct?
Yes, sir.
So for equilateral triangle, that would be A, and sine of 60. So A square sine 60 is root 3 by 2 and then this 2. So 4. So this is root 3 by 4 A square. That is the area of equilateral triangle. So if we put this value in here, so this is root 3 and A. So A is 10 centimeter, which is 10 divided by 100. Similarly, 10 divided by 100 and by, so this part cancels, this part cancels, this becomes again 10, this part is 5, right? So we have M, which is how much? Root 3 by uh, 5 into, oh, why did I get, this is, right. So we have 2 and 10 to the power 3. So this is the magnitude of magnetic dipole. If we put this value in here, so what we will get? We'll get root 3 divided by 2 into 10 to the power 3 into 2 into 10 to the power minus 3, right? So this 2 and this 2 will cancel and we will get how much? This is root 3. Did we miss out something? So did we miss out anything? Oh, so this is correct. So this is 10 to the power minus 6 we are getting. Then we should have got, yeah, did we make a mistake here? 3 by 4 and a square. Right, I was 0.2 ampere. So 3 by 4 and 10 by 100 and 10 by, this cancels. We have 1 by 10, 1 by 10, and this 0.2 will cancel. This is 2 by 4 into 10. So this is 1 by 2 into, yeah, no, this is correct. I guess this is correct. This is a 10 to the power minus 6 Newton meter. Right. So then what is, how can we write this? So this is root 3 into 10 to the power minus 5 into 10 to the power minus 1. Right, guys? So this would be how much? Root 3, and if we take it inside the root, so that is 100 and 10 to the power minus 5. So this is root x into 10 to the power minus 5. So x is 3 by 100 that I'm getting. So 0.2. This is the x that I'm getting. Okay, is this thing clear, guys? Is this thing clear?
yes.
Yeah, then please note down this. And I will send you guys some good works. So you guys please also try this. Okay. If we match this thing. guys please note it down and yeah, tell me if you want me to scroll it down. I've done a calculation mistake in somewhere. Where I have done this calculation mistake? Yeah, so this is 20, right? This is 20 millitesla. So 20 into 10 to the power minus. So that was, this is 20, right? So then this is 10. So then it becomes simple, right? So that was the error that this 20. It was this 10 order, right? So then if I compare this with root x into 10 to the power minus 5, so x is that. So 20 was the magnetic, right? There was this is 20, not 2. Yeah, please correct that and please. Whenever you guys want me to scroll down, please, yeah, whenever you guys have noted